Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics. Today we will learn lecture number 21. Before starting this lecture, let me review what we have done in the last lecture. We started inverse Laplace transform in the last lecture, and then we went on to study the properties of Laplace transform, inverse Laplace transform, and then we implemented this technique to solve Volterra integral equation using Laplace transform method, and we went on to solve integral differential equations when the initial conditions were known. We will continue with the Laplace transform method to solve more equations. So today's lecture outline is solution of ordinary differential equations using Laplace transform method. So we have solved integral equations and integral differential equations in last lecture. So today we will be solving purely ordinary differential equations using Laplace transform method, and then we will solve system of ordinary differential equations using Laplace transform method. And then because we are talking about system of equations, so we will try to solve the system of integral equations as well. Then we will go on to solve partial differential equation using Laplace transform method. All right. So in particular, we will be solving diffusion and wave equations. These equations, we have solved them using separation of variables in previous lectures. So this will give you one more method of solving partial differential equations. So let's start today's lecture with the solution of ordinary differential equations using Laplace transform method. Again, it's very similar to what we have done in the previous lecture. We just take the Laplace transform, isolate the unknown function, and then take the inverse Laplace transform to get the answer. Three-step process. So the Laplace transform technique is one of the powerful tools for solving physical problems involving differential equations, particularly initial value problems. You might have seen in the last lecture that if we do not have initial values, then we may have trouble. The reason is the Laplace transform of the derivative involves the value of the function at 0 at the initial point. So it reduces the solution of ordinary differential equation to the solution of an algebraic equation. This method has a particular advantage in finding the solution of initial value problem without first finding the general solution and then using the initial conditions for evaluating arbitrary constants. It uses the initial conditions right there, so you don't have to wait till end to use the initial conditions. All right, so you don't get, so because your initial conditions have already been used, so you don't need, you will not get arbitrary constants in your solutions. Automatically they will be taken care of. All right, so let's do a few examples. So let's solve some differential equation with given conditions. First example is solve the following ordinary differential equation using the Laplace transform method subject to the initial conditions y0 equal to 2 and y prime 0 equal to 1. All right, so let's see this example. We will solve this with the help of Laplace transformation. So let's take the Laplace transform of the given equation. So take Laplace transform of 1. We obtain Laplace transform of y double prime is s square y. We are using both y bar or capital Y. It's your choice, whatever you want to write. Of s minus s y at 0 and minus y prime at 0. This is the second derivative Laplace transform, plus 4 Laplace transform of the first derivative is s y bar minus y0 and plus 8 Laplace transform of y is just ys, equal to cosine has Laplace transform s square plus 4. Alright. So now if you combine this term, and this term, you will get s square plus 4s plus 8 times y bar of s, and send the remaining things on the other side. This is 2, and this is 1, and this is also 1, 2. Alright, so you got s over s square plus 4 on the right hand side. This is minus 2s will become plus 2s on the other side, and minus 1 minus 8 is minus 9, so this will become plus 9. And now you divide by this left hand side, you will get y bar of s is equal to s over s square plus 4 times s square plus 4s plus 8 plus 2s over 2s plus 9 over s square plus 4s plus 8. Alright, this is what you got. Here you can separate these two terms, 2s over this and 9 over this. S over, if you look at this thing, this is s plus 2 square plus 4, means plus 2 square. So basically this will give you cosine and sine. If s is upward, you will have cosine. If 9 is upward, you have sine. So these two are fine. You can find the Laplace inverse of this term, but Laplace inverse of this term is not possible right now because we have a product in the denominator. So let's solve this thing with the partial fraction. So call this equation star and let s over s square plus 4 and s square plus 4s plus 8 equal to as plus b over s square plus 4. Because it is quadratic, so I have to use as plus b on top. Another one quadratic, so you need to introduce cs plus d at the top. And now multiply by the denominator, you will get as times s square plus 4s plus 8 plus b times s square plus 4s plus 8 plus cs times s square plus 4 plus b times s square plus 4. This is what you got. Now compare coefficients. Comparing coefficients of s cube, because right hand side have s cube, as cube, bs square, cs cube. So s cube is 0 on the left hand side, so you got a plus c is equal to 0. If I compare the coefficient of s square, it's again 0 on the left hand side. This is 4s from 4a from here, b from here, and d, right? Because there is no s square in this term, here it's ds square. Compare the coefficient of s, you will get 1 is equal to 8as, so 8a plus 4bs, so 4b plus 4cs, so 4c. Alright, these are the coefficients of s. And coefficients of 1 means the constants are 0. Constant is 8b, constant is 4d. Alright, so this is what you are getting. So I can write c in terms of a and d in terms of b. d is negative 2b and c is negative a. Alright, so if you plug this thing in these two equations, you will get 4a plus b, d is negative 2b, right? d is negative 2b, so you will get 4a minus b is equal to 0. And from here you have 8a plus 4b and 4c. 4c is negative 4a, so negative 4a will make it 4a. So it will be 4a plus 4b is equal to 1. Alright, and from here it's easy. I used that here and I used this one here. Alright, so I got these two equations. And now from here, if you just subtract, you will get 5b is equal to 1. So b becomes 1 by 5. Right? If you subtract, 4a minus 4a is gone, 4b plus b is 5, b and 1 minus 0 is 1. So this is the value of b. I got the value of b here. Alright, and this will give you D. From B, I can use any of these equations to get A. What is B? B is 4A, or 4A is equal to B. So A is equal to 1 by 4B. So that will become 1 by 20. So A is 1 by 20. Now from here, your C is negative 1 by 20. And from here, your D is negative 2 by 5. All right. So these are the 4 coefficients. So therefore, your Y bar of S becomes, you see here, this star becomes, all right, from star. We have Y bar of S is equal to the first expression, this first expression here, this first expression, this becomes this, AS plus B, and A is 1 by 20, B is 1 by 5. So this is 1 by 20 S plus 1 by 5 over S square plus 4. And then plus CS plus D. C is negative 1 by 20. So CS and D is negative 2 by 5. All right, divided by S square plus 4S plus 8. And then I had these two terms, 2S over this and 9 over this. So you got plus 2S over S square plus 4S plus 8 and plus 9 over S square plus 4S plus 8. So these are the partial fractions. After that we are getting this. Now I need S with this one. So you can separate 1 by 20 times S over S square plus 4, because this, the inverse of this will be cosine 2t. Similarly, plus 1 by 5 will give you sine 2t. So that's no problem. Plus 1 over 5, 1 over S square plus 4. But I need 2, not 1. Laplace inverse will have this 2 square. This is S square plus 2, so 2 will be up front to get sine 2t. So I will adjust that by dividing by 10. That's no problem. Here it is negative 1 by 20 S, and what is this? Plus 2S. How much will that be? See, I can combine this term with this term, right? I can combine these two terms. So minus 1 by 20, 2S minus 1, 2 minus 1 by 20 is what? Okay, minus 1 by 20 S over S square plus 4S plus 8. Let me keep them separate. And minus, this is 2 by 5. So minus 2 by 5 times 1 over S square plus 4S plus 8. And then we have 2 times S over 4S plus 8. And then we have 9 over. All right, I did this one. Right. Now, because this denominator, this is S minus 2, S plus 2 square plus 2 square. Right. So I don't need S. I need S plus 2 everywhere. Whenever we have this thing at the bottom, I need S plus 2. So when you have done this S plus 2, you need to subtract this minus 2 from here. This is a constant term, so 9 minus 2, this is minus 2 by 20, minus 1 by 10. Basically, you added minus 1 by 10, so you can add 1 by 10 here. Similarly, this S should be S plus 2. So this S plus 2 is 4. 2 times 2 is 4, so I can subtract 4 from here. Now I have almost everything, because you got 1 by 20 S over S square plus 4, this will have an inverse, plus 1 over 10 and 2 over S square plus 4, this will have an inverse. So you got 2 minus 1 by 20, so plus 2 minus 1 by 20, this is S plus 2 over S plus 2 square plus 4, and then you can combine this term and this term. These terms will be combined, so you will have plus 9 plus 1 over 10 minus 4, and from here you have minus 2 by 5. This whole thing comes with 1 over s plus 2 square plus 2 square. But because we have this 2 square here, so I should multiply it by 2 and then divide by minus 2 outside. All right, so now I have Laplace inverse of everything. So now take inverse Laplace transform. You will get y of t back, right? Because this is y bar of s. So if you take Laplace inverse, you will get yt back. 1 over 20 Laplace inverse of s over s square plus 2 square, and then plus 1 over 10 Laplace inverse of 2 by s square plus 2 square. All right, and then 2 minus 1 by 20 is 40 minus 39 by 20. Laplace inverse of s plus 2 over s plus 2 square plus 2 square. So that is with the shifting property. It's again the transform cosine 2t but with the shifting property. And then this is 9 minus 4 is 5. So 5, and this is 4 by 10. 5 minus 3 by 10. And Laplace inverse of 2 over s plus 2 square plus 2 square. So now you have Laplace of everything 1 over 20. This is cosine 2t plus 1 over 10. This is sine 2t and plus 39 by 20. This is a Laplace inverse of cosine 2t, but because our origin has been shifted from 2s to s plus 2, so you have to multiply by e to the negative 2t. All right, and similarly this is 50 minus 3 is 47 by 20. So this is plus 47 by 20, and again this is the transform of sine 2t, but origin has been shifted from s to s plus 2, so e to the minus 2t will get multiplied. All right, so this is your answer, and if you want to simplify you can do it, it's your choice. If you want to simplify it, you can write 1 by 20 outside, cosine 2t plus 2 sine 2t. This is yp basically, if you do it with a different method, plus again 1 by 20 is common, so inside will be e to the minus 2t is also common, and by 20, so it will be 39 cosine 2t plus 47 sine 2t. All right, so that is your answer. So that's how easily we can solve. You can say that this is not easy, but taking the Laplace inverse transform, if you have a little practice with the inverse Laplace transform, this is not difficult. All right, you can do it very easily and very quickly. So this is comparatively an easy technique to solve the differential equations, but you should have known the properties of Laplace transform or memorize them very good. Otherwise, if you forget what is the Laplace inverse transform of 1 over s square plus 4, means you are stuck there, right? So of course you have to master this technique. You have to memorize all the Laplace transform of elementary functions and their inverse Laplace transform, shifting properties and stuff like that. Then it becomes very easy to implement this technique to solve any type of equation. So we have found the solution of this ordinary differential equation with initial conditions. So this is basically initial value problem. This is another one written for you. All right, try to solve it. Following the same steps, you can easily solve this one. Again, left hand side has Laplace transform of the second derivative of the first derivative, and right hand side is comparatively easier because exponential gives you just 1 over s plus 1. All right, and t, what t will do? T will differentiate it once. All right. So next is solution of system of ordinary differential equations using Laplace transform method. Solving the system, all right, not just one equation. Here is the system of equations. You see, solve the following simultaneous system because x and y and x both are coming in both equations. So this is a simultaneous ordinary differential equation. that is called the system basically. So using the Laplace transform method, which satisfies the condition 0 and 1, x 0 at 0, 1 and y 0 is 0. So we can solve it using the Laplace transform method, because Laplace transform converts your ordinary differential equations to algebraic equations. So you will get a system of algebraic equation which is very easy to solve. All right. So system of ODEs. So example, dx by dt minus y is equal to e to the t and dy by dt plus x. Alright, so this is a system of differential equation, ordinary differential equations. We need to solve this by using Laplace transform method. So let's take the Laplace transform of both the equations. So Laplace transform of dx by dt minus Laplace transform of y is equal to Laplace transform of et will give me Laplace transform of et is sx minus x at 0, and minus Laplace transform of y is capital S, let's call it capital S, and Laplace inverse of Laplace transform of et is s minus 1. Similarly, Laplace transform and Laplace transform of second one is dy by dt plus Laplace transform of x is equal to Laplace transform of sine t. So this is s capital Y s minus y0 plus capital X s is equal to sine transform is s square plus 1. Now what is x0? x0 is 1 and y0 is 0. So this is gone. So you got a system, you see, sx minus y is equal to 1 over s minus 1, and this 1 will be added on the right hand side. And then you have x plus sy is equal to 1 over s square plus 1. So you see, you got a system of algebraic equations, right, in x and y. There is no derivatives involved. This is s1 plus s minus 1. So this is s over s minus 1. So this is a system of algebraic equations now. System of algebraic equations in x and y, capital X, y. This has become the system of algebraic equations in capital X and y. So if you solve for x and y, what you can do is either you can multiply by s and add, right? Let's call it 1, let's call it 2. So if you multiply 1 by s and add in 2, you will get s square plus 1 x, and this sy and sy, they will be cancelled, and this will be equal to s square over s minus 1 plus 1 over s square plus 1. Right? So x is y is gone, so you got x only. So your x becomes s square over s minus 1 s square plus 1, and this is 1 over s square plus 1 square. Alright. Again, using partial fractions, you have to rewrite this into separate forms. Alright. You will get a over s minus 1 and b s plus c over s square plus 1. So just verify that this expression by using partial fractions, you will get 1 over 2 So this is what you will get for this expression, and plus 1 over s square plus 1 square at the end, which is coming from here. So you can verify this, all right? You can easily verify this step by using partial fractions clearly. Now you can clearly take the Laplace inverse transform from here, all right? This implies small x of t will be equal to Laplace inverse of this whole thing, 1 over s plus 1 plus s over s square plus 1 plus 1 over s square plus 1 and 1/2 outside, and then Laplace inverse of 1 over s square plus 1 square. Okay, this is the product of 1 over s square plus 1 and 1 over s square plus 1, right? Product of two functions. And I know the Laplace inverse of the product is the convolution, right? Convolution integral. So one way of doing is that you can find the convolution integral. So answer is basically Laplace inverse of 1 over s plus 1 is just e to the minus t plus Laplace inverse of s over s square plus 1 is cosine t and plus sine t. This is one thing. And the Laplace transform of this thing should be 1 over 2 sine t minus t cosine t. Alright, you should verify this. This is very clear, but you can verify this. Alright, verify this, that Laplace transform of this is given by this expression, sine t minus t cos t. You can either use convolution because it is the Laplace inverse of the product of two Laplace transforms, or this may be the derivative of something. The derivative of 1 over s square plus 1 is 1 over s square plus 1 square, but 2s will come up front. So maybe if you can adjust that to s, you can use direct methods instead of convolution. Alright, so this will be your answer for x. So you got xt. But now I need yt as well, not just y. So from here, if I need y, and then what I will do? I will multiply this by s and subtract. You see, I will multiply 2 by s and subtract. Alright? So now 1 minus s times 2 gives me sx minus sx is gone, minus y minus s square y. So minus 1 plus s square y is equal to s over s minus 1, and this will be s over s square plus 1 minus s over s square plus 1. This is what you get in this case. So your y of s is equal to divide s square plus 1. So you will get minus s over s minus 1, s square plus 1, and minus plus s over s square plus 1 square. Alright, Laplace inverse of this is easy, but here you need partial fractions. So again, using partial fractions, you can write. So I can just write it for you, and you can verify that. After partial fractions, I'm writing this last term first because it is with the positive sign, and minus, it is 1 over 2, and I think it is the same thing, isn't it? Here, s square over s minus 1, s square plus 1. No, here it is s over s minus 1. There is a difference. Alright, there is a difference. So you will get 1 over s minus 1 minus s over s square plus 1 and plus 1 over s square plus 1. So this is what you are getting. So the answer to this left hand side is 1 over s t sine t and minus 1 over 2. This is e to the minus t minus cosine t and plus sine t. So this is your y of t. I took the inverse Laplace transform. Alright? By taking inverse Laplace, so you got the solution of x as well as y. So you got the solution of the system. So therefore, the solution of given system is x of t and y of t. Alright, so if you want to write it again, I can do it. Sine t minus e to the minus t plus cosine t plus minus sine t. This is your solution, and xt was, again 1 by 2 is common over there as well. So e minus t plus cos t plus sine t plus sine t, and then you have sine t minus t cos t. This will become this will become 2 sin t. Instead of writing separately, you can write 2 sin t. All right, so that is your solution of the system by using. So what we basically, what is the benefit we get from the Laplace transform is, this was a system of differential equation. After taking Laplace transform, we got a system of algebraic equations, and solving algebraic equation is much easier than solving differential equations. All right, so we solved for x and y, and then taking Laplace inverse transform to get the solution. So as we applied this Laplace transform method to system of differential equations, this can be done for integral equations as well. In previous lectures, I have solved integral equations with the help of Laplace transform. So again, if it is a system of integral equations, you can do it easily, because you have to take the Laplace transform of both equations separately. They will give you the algebraic equations, solve them simultaneously, take the inverse transform, and get the solutions. All right. So the same procedure can be applied on the system of integral equations, which is solve the following system of integral equations, and it is really not difficult. We have solved these type of equations separately. All right, but only difference is, see, u1 and u2, u2 and u1, they are appearing in both the equations. So you will take the Laplace transform of first separately, Laplace transform of second separately, solve for u1 and u2. You will get 2 equations in u1, u2, solve for u1 and u2, take the inverse Laplace transform, and get the solution. It will be very, very easy exercise for you guys. So let's take this as a homework. Solution of partial differential equations using Laplace transform method. Partial differential equation, again, on the same steps, on the same footsteps, we can solve partial differential equations, because only thing is Laplace transform just reduces the derivatives, right? It just replaces the derivative with the algebraic expression. So what we will be doing in the partial differential equation is, in partial differential equation you have partial derivative with respect to x and t. So when you take the Laplace transform, it will convert one derivative to algebraic thing. So it means the second derivative will remain there. So this technique converts partial differential equation to ordinary differential equations. And ordinary differential equations are much easier to solve, right? So solution of partial differential equations using Laplace transform method. So before going to that, we have to redefine our Laplace transform for partial derivatives. It's exactly the same thing. The partial derivative and Laplace transform, the property of Laplace transform of the derivative is exactly the same. Laplace transform of the derivative is su minus ux0. Now because there are 2 variables, so t is going to s, not x. X will remain there, t will become s, and of course when you pick the value, you will pick the value of t at 0, not of x. All right, this is the only difference. You have to be careful in writing these variables. Similarly, the second derivative will have s square u minus su0 minus u prime 0, but 0 is for t, not for x. Now Laplace transform changes t to s. So x will remain x. So what we will be doing is, when you take the Laplace transform of the x derivative, it will just take the derivative of your Laplace transform. Then you will not use this formula. All right. Then with respect to x, you just take the Laplace transform of u and then take the derivative. All right. Similarly, the second derivatives. With partial derivatives, it will be different. Partial derivative, one time derivative uses this formula, other derivative uses this formula. So you have to mix up the formula. So these 5 formulas will help you solving partial differential equation with the help of Laplace transformation. So again, there are 2 problems: solution of diffusion equation, which is heat equation subject to initial conditions, and solution of wave equation, which is given by this. Solution of wave equation subject to these conditions. So I will be solving one and you will be solving the other one. All right. So let me solve the first one, the diffusion equation or heat equation, and you can do the other one, or maybe I can do the second one, whatever is difficult. All right. So solution of the diffusion equation, you solve this with the help of Laplace transform. Just see how I do implement this technique on the wave equation, this equation. This is a non-homogeneous wave equation with one zero boundary condition. Other boundary condition is u is bounded, because you see here x goes from 0 to infinity, not to L. So your problem is comparatively easier because you have a boundary conditions here. Very easily you can implement them. All right. So let me solve this wave equation, and I'm leaving the diffusion equation for you guys. I hope you can do it easily. In lecture notes you will see both the solutions, so don't worry about it. So these are your boundary conditions, these are your initial conditions. So this is your wave equation, we need to solve it. So solution is, first we just take the transform of the PDE, all right. Take Laplace transform of star, we obtain uxx gives you, uxx will just give you the second derivative of your Laplace transform with respect to x square is equal to 1 over c square, and here I will use that formula that s square uxs and minus su small u at x0 and minus ut at x0, because the derivative with respect to time, minus what is the Laplace transform of cosine? It's s over s square plus omega square. All right. So ux0 is 0, this is gone. utx0 is 0, this is gone. You see these two conditions, these both are 0. So what I got is d2u by dx square minus s square by c square u is equal to minus s over s square plus omega square. All right, this is what we got. So this is, you see, this is an ODE. This is an ODE in u and x. All right. So this is an ODE in u and x. We will treat s as constant. All right. We will treat s constant here because derivatives are with respect to x, and these are ordinary derivatives. So s is a parameter here, as s is fixed. All right. Ux is variable here. All right, and s is a parameter, so we will assume it fixed. All right. So what will be the solution? I need to find the auxiliary equation for yc. It is m square minus s square by c square is equal to 0. So this means m is equal to plus minus s by c. So therefore uc, the complementary function, is c1 e to the power s by cx plus c2 e to the power minus s by cx. All right. And for yp, you can use any method, maybe variation of parameters and stuff like that, because the right hand side is not 0. No, it's a constant. The right hand side is a constant for x. So what you can do is, for yp, let your yp be constant, constant a, then not yp, up. Then this one, equation 1, becomes 0 minus s square by c square a is equal to minus s over s square plus w square. Because you see there is no x, that's why we are treating this as constant. So what is your a here? So a is c square over s times s square plus omega square. This is what you got. So your up is this. So this is your up. All right. Now uc and up, if you add them up, that is your solution. So therefore u is equal to uc plus up. So uc is c1 e to the minus s by cx, sorry, plus, and c2 e to the minus s by cx, and then plus you got c square by s times s square plus omega square. So this is your solution. Now the boundary condition. Our boundary condition was u 0 t was 0. So if you take the Laplace transform, capital U 0 s will be equal to, what was the Laplace transform of 0? It was 0. So it means the same boundary condition. So when x is equal to 0, this implies x is equal to 0 means c1 plus c2 plus c square over s, s square plus omega square is equal to 0. This is one case. The second is, second condition was that u is bounded as x goes to infinity. So if u is bounded, then capital U has to be bounded as well. If u is bounded, its Laplace transform is also bounded, right? So this condition implies that your c1 has to be equal to 0. Why? Because as x goes to infinity, this thing will go to infinity. This thing is going to infinity as x goes to infinity. So to keep my solution bounded, I need to make this c1 equal to 0. Otherwise, this solution will be unbounded. All right. So c1 is equal to 0 here as well. So c2 is equal to minus this one. So therefore, your u x s is equal to, c2 is negative of that. So if I take this as common, I will get c square over s times s square plus omega square and 1 minus e to the minus s by cx. This is what you will get. Now you can take the Laplace inverse transform to get the solutions, right? So we use the conditions on x only. We cannot use the conditions on t right now, because the reason is this is an equation in x. So I have to use the conditions for x, which is at x equal to 0 and at x equal to infinity. All right. So now, so take inverse Laplace transform. So by taking Laplace inverse, you will get uxt back, and Laplace inverse of this thing, and Laplace inverse of this thing with e to the, so this e to the c by x, s by c will only shift your function. So remaining part is the same. You see, the remaining part is the same. So Laplace transform of this is, you can easily verify. 1 minus cosine omega t. All right, and if what we did is with the help of partial fractions only, you can write partial fractions a by s plus b s plus c over s square plus omega square. So write this in terms of this, find a, b, c, and take the Laplace inverse. You will get this, because you see Laplace of 1 over s is 1. And Laplace of s over s square plus omega square is cos omega t. It means your c will be 0. Right? It means c will be 0 when you find the partial fractions. And this is the only shifting. You see, 1 over s square plus omega square is the same thing. By multiplying by this exponential, you will just shift the origin. So Laplace transform of this will be 1 over omega square again, but you will shift the origin. 1 minus cosine omega t will be shifted to, because you are multiplying this by x by c, right? So this will change your t from t minus x by c. But you know that when you shift your origin, this is the second shifting property, you multiply by the Heaviside function, which is t minus x by c. So that's the Laplace transform. So c square times this minus c square times this will be your solution. So this is your solution of the partial differential equation. All right, so again, see, separation of variable took lot of time to find the solution of the wave equation. But here Laplace transform gives you a very quick answer. All right. So similarly, when you solve the diffusion equation, you will see that by implementing separation of variable technique, it will take a lot of time, and Laplace transform gives you the answer straight away. And one more thing, if you observe, this is a non-homogeneous wave equation. You see, there is a non-homogeneous term here, and we have not solved this non-homogeneous with separation of variables. So Laplace transform actually takes care of these non-homogeneous terms as well. All right, so that's why it's a better method, and of course very useful in all types of equations: differential equations, integral equations, and integral differential equations. We can solve all three equations with the help of Laplace transform method. So today we solve our ordinary differential equations with Laplace transform, system of ordinary differential equation, and system of integral equation with Laplace transform, and finally we solve the partial differential equation with the help of Laplace transform method. So next time we will start another integral transform, which is called the Fourier transform. We will start Fourier transform and see how that goes. So till then, Allah Hafiz, Assalamu alaikum.